Why does water freeze when you place it in a freezer? I'll give you a clue. It's not because the freezer is sucking the heat out of it, whatever you might have heard. The answer is entropy, and in this video we are going to look into the fundamentals of entropy, the true driving force of all spontaneous processes, both chemical and physical. Entropy is a property of matter, just like density. We can think of it as a quantity associated with the randomness or disorder or the chaos of molecules and energy in a system. And it has the symbol S. So S for entropy. Why it's an S, I have no idea, but S it is. Maybe it's for spontaneous. So spontaneous processes are those that once we've started, they're going to continue to happen without outside intervention. And when we've got a spontaneous process, there is always an increase in the disorder of the molecules and in the random distribution of energy in the universe. This is essentially the second law of thermodynamics. So change in entropy for a spontaneous process is the result of the entropy of the final state, take away the entropy of the initial state. And that has got to be positive for a spontaneous process. Let's start by looking at entropy changes in physical processes. Imagine I've got a glass bulb and it contains a gas. So that would be bulb number 1. And it's connected to a second glass bulb. And in my second bulb, I have got a vacuum. So the first one contains my red gas. Second glass bulb contains a vacuum. And they're connected by a tap, which at the moment is closed. What is going to happen when I open the tap? Well, the gas is going to expand to fill the whole volume that's available to it. And that's a spontaneous process. Now, in this particular example, there is no change in energy, but the molecules now occupy a far greater volume. So there's more disorder. There are more ways of arranging the molecules and their associated energy in the total space available. The entropy change for the process is positive, and the process being expanding the volume and allowing these molecules to move from one glass bulb into the combined space. Moving on to my second example. I have got a hot metal block. Let's say the temperature of that block is 100 degrees C. And next to it, but not touching, I have a second block. This block is cold. It's got a temperature of 0 degrees C. What's going to happen when I move my two blocks together so that they're now in close contact? Well, I'm sure we can appreciate that the thermal energy is going to spontaneously be shared across all the atoms. And since this is a much larger number than before, the energy is now distributed over a much larger volume, and it's going to be more disordered, it's going to be more chaotic, more random. The entropy change with this process, once again, is positive. Now, this is a point at which we need to get a little bit more specific. For a spontaneous process, the entropy of the universe must increase, not just the system. So we can think that our metal blocks are my system, and everything surrounding my metal blocks are, strangely, going to be called the surroundings. There we go, surroundings. So for a spontaneous process, we require the total entropy change to be positive, and the total entropy change is sometimes known as delta S universe and sometimes known as delta S total. We can determine or calculate the total entropy change by adding together the entropy change of the surroundings with the entropy change of the system. Moving on to look at a chemical process. This is the reaction between gaseous ammonia and gaseous hydrogen chloride. And when you put the two gases together, we see clouds of white smoke of ammonium chloride, as you can see in my nice photograph here. So my reactants are in a state of high entropy. We've got a high disorder of molecules because both the reactants are gases. My product, in this case the ammonium chloride, is in a state of low entropy because it's an ionic solid and the ions are in a regular crystalline arrangement with little disorder. The entropy change of the system, i.e. the actual chemical reaction, in this case, is going to be negative. We've got a decrease in entropy, a decrease in the randomness or disorder of the molecules and the energy in my system. And yet, this is still a spontaneous process. So how are we going to explain what's going on? Well, the reaction between gaseous ammonia and gaseous hydrogen chloride is highly exothermic, as strong ionic bonds, if I could get it right, strong ionic bonds between the ammonium ions and the chloride ions form. And this energy moves from the system, i.e. our chemical reaction, out into the surroundings, as we can see indicated by my red wavy arrows on the picture here. The molecules in the air are absorbing this heat, which means that the temperature of the surroundings is increasing. Maybe I should write temperature of surroundings is increasing. Not only have we got more energy to distribute in our surroundings, we also need to remember that our air molecules are moving around faster because they've got more energy. So their disorder is increasing as well. However we look at it, there is an increase in the entropy of the surroundings. So we can say here that the total change, or the entropy change of the universe, is equal to entropy change of the surroundings plus the entropy change of the system. We know that the entropy change of the system is negative, but because this is a spontaneous reaction, I know that the total or universal entropy change is positive. So the entropy change of the surroundings not only is positive, but it must be sufficiently positive to compensate for the entropy change of the system being negative. So let's pull this together. If I've got an exothermic chemical reaction, then I know that my system is giving out heat to the surroundings, so the entropy of the surroundings must increase. It's positive. And in the case of an endothermic chemical reaction, clearly we have the opposite happening. The system is absorbing heat from the surroundings, so the entropy of the surroundings must decrease. It must be negative. Let's return to our original question. Why does water freeze when we place it in the freezer? Well, we've got water molecules in the liquid state turning into water molecules in the solid state, i.e. ice. During this process, we get strong hydrogen bonds formed between the water molecules that start to lock them into our solid lattice. Water freezing is an exothermic process. We know that for this process, delta H is equal to minus 6010 joules per mole. And we also know that the entropy of the system must be negative, because in ice the water molecules have got less energy to distribute amongst themselves, and they themselves are not free to move. The system is overall becoming less ordered, less chaotic, and less random. But we know from everyday experience that this spontaneous process of water forming ice in the freezer is only going to happen at temperatures less than 0 degrees C. So the total entropy change, so total, or it could be universe, equals the entropy of the surroundings plus the entropy change of the system. Okay, so we know that if it is below 0 degrees C, this is a spontaneous process. So total entropy change must be positive. But we also know the converse is true. Above 0 degrees C, this is not a spontaneous process. So the overall entropy change is negative. Now we know that the entropy change of the system for water forming ice is negative. We've just explained why that is. And we know that since it's an exothermic process, the entropy change of the surroundings is positive. That energy is moving from the system into the surroundings. So what are we saying here? Essentially what we're saying is that the heat released during this exothermic process, so delta H is negative. Let's just remind ourselves again. So that means it's exothermic. And delta H here is for the system. Let's remember. So the heat energy released is only sufficiently increasing the entropy of the surroundings to the point where the overall entropy change is positive if the surroundings are cold enough to begin with, i.e. if it's less than 0 degrees C. I'm going to stop at this point and give you an analogy which I hope will be helpful. Imagine you've got £10 in your bank account. If I give you another £10, your overall worth has doubled. It's had a significant impact, that tenner. However, if you had £10,000 in your bank account and I gave you £10, your overall worth has not increased noticeably at all. And it's exactly the same with energy. If the surroundings are cold, then adding a little bit of energy has a big effect on increasing the entropy of the surroundings, i.e. in terms of the amount of energy and in the fact that the molecules are moving around faster, more disorder. But if the surroundings are hot and we add the same small fixed amount of energy, we get a far less significant increase in the entropy. So let's pull that together. The entropy change of the surroundings is equal to the heat absorbed by those surroundings. Just about squeeze that in. Divided by the temperature of the surroundings. Now, if we're working under constant pressure, which is pretty much always the case as chemists, then this heat change here is identical to enthalpy change. So we can say that the heat change or the enthalpy change of the surroundings is equal to minus the enthalpy change of the system. Why? Because if the system, our chemical reaction or physical change, is releasing energy, then this exact same amount of energy must be moving into the surroundings and increasing the enthalpy here. And we can say that the entropy change of the surroundings is going to equal minus the enthalpy change of the system divided by the temperature. So our units of entropy are going to be joules per Kelvin per mole. Pulling all that together, we can say that for a spontaneous process, the total entropy change needs to be positive. And we can figure that out because it is equal to minus the enthalpy change of the reaction divided by temperature plus the entropy change of the system, of the chemical reaction. And we can calculate the entropy change of the system because it is the sum of the entropy of the products take away the sum of the entropy of the reactants. Now, luckily for us, the absolute entropies of many substances have been determined, and we can simply look them up in our data book. Let me give you an example. So let's have hydrogen reacting with oxygen to give us water. Now, if I go to my data book, I can look up the entropy of hydrogen, and it's quoted for 298K, and it is 130.7 joules per Kelvin per mole. I can do the same for oxygen. Let's put that one over here. That comes out to be 205.1 joules per Kelvin per mole, and water is 69.9 joules per Kelvin. Oh, it's a bit of a squish here, per mole. Okay, so the entropy, total entropy of the reactants is going to equal 130.7 plus half, because it's only half O2. These are per mole, remember these values here. So it's 205.1 is the entropy of a whole mole of oxygen, but I only need half for this calculation. So 205.1. And the total entropy of the products is equal to 69.9 joules per Kelvin per mole. So if I put all that together, products take away reactants, I come up with the entropy for this system as written in the equation is minus 163.4 joules per Kelvin per mole. And it's a negative. And that's what we would expect, because I have gases reacting together to form a liquid. So less energy and less disorder in my system. As always, there are notes and practice questions over on the Crunch Chemistry website. There is a link somewhere in the blurb below. And if this has been helpful, then please subscribe and hit the like button. It makes a big difference to a small channel like us. It is an effortless way to help support your studies and tell everyone how great we are. Spread the word. Look forward to seeing you next time.